Okay, maybe a few questions ahead, maybe a few hand rises. It's like, who already is familiar with Python? Maybe raising the hand shortly. Almost everyone. Who uses Conda environments? Half, okay. Who managed to download the data? 3, 4, 5, 6. Okay, maybe that's one of the first steps to do. Who could clone the GitLab repository already? It's like 1, 2, okay, a few. Okay, maybe we need a little bit of time to organize that. Maybe we should do that now. You saw the mails we sent around. Maybe we start with the downloads from Google Drive. It's like so that we can get that running while Pablo introduces the first part. Yeah.
No. Okay. So I hope you got the GitLab link. If not, raise the hand. Moritz will come to you. If you didn't get any email about GitLab or Google Drive. And if you did, you can just go through the README in GitLab, and there would be this first link is for all the notebooks that you need for the tutorial, and also the Conda environment is everything there. And then you just follow these instructions to install all the libraries and packages that you need. And maybe you can also download here the data is netcdfs. This should be quite quickly. The second one is a little bit larger, so it may take some time. But if you haven't done this yet, it would be nice to do that. That's not very sharp, is it? Well, okay. Anyways, yeah. If you have any questions, raise the hand, and Moritz can come to you. Okay. Good. On the tutorial, what we have planned is partially introductory because some of you haven't used Python that much, and then there's something online already. Sure, I can. There you go. So it will be even just going through Matplotlib with easy 2D plots and also color maps with Matplotlib as well. Then using X arrays to read in netcdfs and also plot them, do some animations. More questions? Thank you. Okay. And then I will show also 3D plots, partly with Matplotlib, but also with here Plotly. Plotly basically can do more or less the same as Matplotlib. The only advantages which I will show is volume plots, 3D volume plots. That is with Matplotlib is just a pain, and Plotly is a little bit nicer. And then for interactive plots, half-out HV plot, sorry, is quite nice, but it's a little bit slow. So I don't use it that much, but just that you know, it's the possibility. Yeah, you want to say?
Yeah, and the second part will be more about working with large data sets, which are stored on unstructured grids. And there's several approaches we have. I wanted to show a few. One which you most likely know already is scatterplot, which is the easiest way to do it, but also the worst way to do it. Then there's other techniques, for example, the data shader, which you can see here, which is basically working like a histogram function, which is finding to a particular bin particular values and uses those ones to visualize the data. We have a notebook to use the data shader. Another approach is to consider also, well, the basic question when you work with unstructured data sets, which already when you work with large data sets, how many pixels do you want to plot? For example, if you imagine that we now run icon simulations which have 70 million grid cells per level, and that your latest Mac with a 15 or 16 inch screen maybe can resolve 15 million. So do you really want to plot all of them, which you are not even able to show? So figure out how many pixels you want to plot and how many pixels you can show. So that's we will have some thinking about that as well. So it's like, for example, if you plot the whole globe, the whole sphere, you need different pixels and you don't need all of them. However, if you go to closer filaments or structures you want to analyze, it makes sense to go to the original, the native grid. So we also have a short notebook on using the to plot on triangulars. And another version is also how to make life simple to apply typical techniques, is bringing unstructured data to regular grids. So we have some interpolation schemes there, and we will also connect it to a task, depending a little bit on how far we get.
Okay. So by now, I hope everybody has downloaded everything, and we can just go to the code.
Everyone found the GitLab link already? It's like, is there anyone who did not found the link? It's like, you could not clone it?
Go to Google Drive. It's better. It's faster.
Yeah, we have problems with the GitLab server at the moment. It's a bit slow. Maybe, but there's a Drive link to also clone, to download the GitLab repository. Do you know where it is?
You can maybe go to him.
Yeah.
Yeah. Okay. For the rest, I guess you have like a Python interpreter, like Jupyter Notebook, Spider, whatever you use, right? If, yeah. So then I would ask you to open the first folder, which is 2D time series. And there you find these two notebooks. One is for ray tracing and the other is just a simple energy balance model. You can choose either one of those. I thought because some of you are not so familiar with ray tracing, I show it too. But basically it serves for the same purpose. It will be just for plotting some lines and that's it. So there is a little description on the left on the energy balance model about the model itself. If you're interested, you can read through it. But we are more interested about the plotting. So what we will use is basically just matplotlib. Okay. Here, these are the functions for the model which you can run, and then we call our first plot already. So how you structure the plot, the code is quite easy to follow. Is first you call, you define a figure with pl.figure. You say like, say? Yeah. Yeah. Okay. So yeah, you define the figure as an object and define like the size of it. You can change it. There are a few other arguments that you could put in, but this is basically like an easy plot. So yeah. And then you would here that's calling the two lines that you are plotting in the figure. One would be here with a color red, the other one blue. Both of these are the same thickness, so like 2. And then you put some labels. The good thing is you can also, I mean, it works with LaTeX LaTeX font, or so it will compile it, right? So it looks like a proper equation. Then, if necessary, you can also put the limits for the x-axis, y-axis. If not, it will be automatic, right? And then also label your axis. Here again, if you want to put some LaTeX equation, it also works. And for the title as well, right? Here I have some equations, so you see that it's plotting the correct thing. And the legend, so for each plot, we put a label, and then the legend will show it in the plot, right? And you can say where you want to put the legend, and yeah. And then you always call plt.show, so you plot the actual plot. And then you should get something like this, right? So we have the two lines with the legend on the top left, the title, you see that is a LaTeX equation which works and is just nice and easy, right? And for the ray tracing thing, it's basically the same. So here we're calling a little bit more things. Actually, XArray, you don't need it here. Yes, SciPy is just for a special function gamma. And then here is again the model, the equations we already explained it through these weeks. Blah, blah, blah. And then here you're calling some plots, right? Here actually we are doing subplots. So it's a plot which has various plots in it. So the way to do it is here you can define the axis of each plot. There would be like two plots, one next to each other, and you are sharing here the x-axis per column, and you share the y-axis everywhere, right? And then you just let the model run here with these are just the initial values for the run. And then okay, this is a little bit more complicated, the plot, but it's just some lines that you add, right? So fill between x would be if you have two lines in a space in x along the x-axis, it will be filled with some color. Here, light color. If you see the plot, there is some color between the blue lines, right? So that is the area that we're filling with that function. Then V line is a vertical line. So for example, if you have a spectrum of the internal gravity waves, you can do V line at the Coriolis frequency, and then you have like a straight line. So here is actually F, what I'm plotting. So is this line here, is the V line. Then you have plot, which I already explained. Both plot, a scatter plot, which is just a dot. So the difference is a scatter plot, you can put a 1x to 1 epsilon. For a plot, you need like a line. So you need an array against an array. And then for the subplots, the commands change slightly. So because you are putting labels to a specific axis, so you have to always call for the axis first. And then instead of .x label, it will be .z lower bar x label. Yeah, and then I find this function to be useful because if not, you have to care for the correct spacing between the subplots and so on. And you should just put tight layout, it will take care for you. So it's then automatic. So how it looks like is then like this. You have the two plots, and then yeah, what we have plotted is the Coriolis frequency here. Here we have stratification, which changes with depth. We have omega with time, so it's the ray that's following this path. And then the starting omega is this dot that we plotted, and then the Doppler shift, which the wave is filling. And that is for one initial condition, and then you have the second one here. Now you also see that one legend is in the bottom and the other one is in the plot. That is just, you can define the location of the legend, like here. This would be just right below the plot. So it's location at the center, then box to anchor is where you want to anchor the plot, the legend, and then n calls 5 is that you have 5 columns of the legend, right? Okay. So I hope that has worked for all of you that have tried. And then the next thing, well, this is again some subplots. You can just go through the notebook. And then the next thing I wanted to show is like a simple animation. Yeah, so for the animation, we are still using matplotlib.animation. Okay. Are you following? Did you manage to plot everything that I showed? It's just running the code. Yes, I got a yes. Okay. Okay. So yeah, for the animation, It's basically
Pablo?
yeah.
I think we should give some short time to set up the environment.
Yeah, still problems.
Yeah, yeah, we are a bit behind up here. It's like
okay. Should I come up too?
No. Yeah, well, we maybe do 10 minutes to set up the thing. Then you can listen better to Pablo what he's doing. It's like
But the first part is anyways introductory. Okay.
Yeah. Or you want to finish that part?
Yeah, because then I come to the exercise, and then the ones that are further ahead, then they come
okay
with it.
Okay.
Sorry. IT max is not defined. Okay. So here you have to run. Here I'm setting IT max. So these are the initial conditions. To run from up
from
down.
the beginning. Okay.
Yes. Please.
Okay.
And then it should work.
Yeah, let me check it and then
Okay, so the last part of here, the matplotlib, is just the animation part, which is still done with matplotlib.animation. And you can display it because it's a notebook, so you need like something to display it with, and we will use here IPython display with HTML. It depends, depending on which Python interpreter you use, you will need another function, but for notebooks, this is a good one. So how it works is basically the same. We are still calling a figure, defining an axis. Here I do it with a subplot, could be also like a figure, normal figure. Then we are running the model. I'm doing some spacing, so I'm not plotting all the output, just every 100 steps. So it runs faster. And then I plot just the first time step with the first value. And I save it, no? Because it's a dot plot, you would need an array, but by calling here the 0, you save just the first dot, okay? Then these are just some specifications for the plot. It's not so important, but then the important part is basically this function, which is the update function, and that you will call every time that you want to update the plot and like follow the array a little bit further, right? So it's you're counting your frames. Let's say you have 10 frames, and then every time you would call the second, third, fourth frame and update it. And then the function that is calling this update is the animation.func animation. So you're calling here your figure, the figure that you defined above, right? And then your update function, which might vary depending on what you want to animate. If you look then at the other notebook with ray tracing, it looks slightly different as we want to plot more things. And then you run it for the time of your simulation, in this case, the length of t. And then the interval is the actual time that you want to have between each frame. Okay, so here I put it to 30, which is like a normal movie should be more or less. If you want it to be much faster, then you decrease it, and if not, you increase it. Okay, and then finally you just display the animation, and then it looks something like this. This is okay. You press play, and you see it's going. Okay. Here, as you see, also the title has been updated. You have to see if you should define your axis too, because if not, it will change and the plot changes a lot and it's a little messy. Okay, and for the ray tracing, it's the same. So here there is an exercise. So you can create. Okay, this is just for creating a subplot. You can try to do that. You should come to this solution. You can also put some text, I don't know if you want to highlight something, and you can do it. So this is one exercise, and then the second part here is again a simulation of subplots, which is basically the same. You can go through it and try to do it yourself, and then you come to something like this. You see everything is moving. So here again, as well, this orange line is moving, although you cannot really see it. It's just bouncing up and down the ray, okay? And then that's it. So you can maybe go through it, and the people that need some help, just raise the hand. Okay, so how far are we with the first part, with the 2 notebooks? Did you manage to go through it? Are there any more questions? No? Seems like everybody is good.
Maybe before, who's having already a running environment? Hands up. 1, 2.
Don't be shy.
Don't be shy, please.
Hands up.
There's some running environments here still. Who's having a running? Who can run the notebooks already?
Okay.
Yeah,
okay.
yeah. Okay, that's a lot. A few. Okay, Pablo. I think you can continue. I help the others.
Yes. Okay. So, are there any questions about the animations, about the subplots? Anything? No. Then I think we can already move on to the next one, which I would say is the matplotlib and plotting color maps with it. So for that, we will need the netcdf that we send it around in Google Drive, right? I hope you could install it. It's the one that is called snap.cdf. And we will read it with xarray, okay? So although with xarray, you can also do some plots, and I will show it in a minute. But you can also do the contour plots or your 2D plots with the color maps with matplotlib. So we will use, no, okay. So here we are importing why is not showing what I'm showing? It's going very slow. Oh, okay. Anyways, we are importing matplotlib. We're importing colors from matplotlib, so we can define some color maps. And we then read in the netcdf with xarray, like xarray.open dataset snap.cdf. And then, as you see, the xarray already has some encoding, so it will recognize what is the x-axis, or the x dimension, y dimension, z dimension, also time, and then the different variables. So we have u, v, w, b, and p. So what this CDF is showing is a field of eddies which are balanced and they are interacting with themselves, but it's always only the balanced part. So it's only eddies. There are no waves whatsoever. It's just eddies. Okay, and it runs for a few times. So you can see, for example, here, this is the time that it's running for in seconds. And then here is the description of the x dimension and so on. This would be in meters. Okay, so we have read everything in, and we can now plot the first part. So here again, I'm doing subplots. So plots which will look eventually like this. Okay, so these are some color maps, and I'm calling different functions to show them. So the first one is a p-color mesh. So that's basically plotting pixels, squared pixels with different colors, which are coded with a color map. Okay. So now what we are plotting here is vorticity, is the vorticity of this field at one specific time step. Okay, so it's a snapshot against x and y. Okay. So on the left side, you see it's not quite smooth because these are kind of squares of pixels that you're plotting. On the right-hand side, we have another function that we're calling, which is contour f. So it's like field contours. So that's the function itself is gonna somehow interpolate a little bit. So they are looking for iso lines of same vorticity values and then plot some contours. Okay. If you don't want to fill the contours, you can just use the contour function without the f, and then you have here just specific lines, okay? Here again, they are color-coded, they are showing the same field, but you see that between the lines there is white spacing, they are not filled, okay? Okay, and then another issue maybe is the color bar, right? Here we have a lot of zeros, we have 0.0002, and that is maybe not so nice to see in one plot. So we want to fix it and maybe put like a scientific notation, right? So we have some power like 10 to the minus 4 or whatever, and that we can do it for the color bar. So, okay, I'll go quickly through the code. So again, here we are defining an object, that's the figure, which would be subplots, and we have some axes. So before I showed here that we were defining the axis with a parenthesis, and then axis 1, axis 2, axis 3, and so on. Here we're just defining all of them at once. Just later on, we have to put some indices for each axis. So 0, 0 is the upper left plot, and then 0, 1 is the upper right plot, 1 and 1, 1 would be the lower right, and so on. Okay? So here I'm computing the vorticity at one specific time. This is just the index at time 3. This is depth, so it's at the surface, and then against x and y. And I do the differentiate against x and differentiate against y of v and u, and I get the vorticity, okay? And now here is the p color mesh, so it's the is this plot here, right? With the squares as color-coded squares, basically. So how it works is, so you put the axis that you want to plot it in. So it's the 0, 0 is the upper left plot. Then call p color mesh, and then here you're putting your x-axis values against your y-axis values, and then the vorticity is the color map. So it's basically like the set direction for the 2D plot. Then you define a color map, which here is blue, white, red. So it will go from blue, then at 0, hopefully is white, and then red. And to make sure that the white is at 0, we define the boundaries of our color map. So it's the minimum value of the vorticity, which is, well, here I do the absolute value of the vorticity and then look for the maximum and then do the negative of that. And then the Vmax is the positive of that. So we have it bounded, and we show all the colors. If you don't do this, then your color bar is somehow shifted, and the white part of the color bar might not be at 0. And that's not so nice. Okay, and now here we set the labels for the x-axis, y-axis, and the title, and put the color bar. So in the color bar, we say that we want to do the color bar for this object, which is the p color mesh, is our plot. We have to define the axis so that each subplot has its own color bar, and then the label, okay? The function for the contour, the field contours is basically the same. You just change contour F instead of P color mesh, and you should get the same. And now here is the explanation for the color bars, how to add this scientific notation. So if you do the normal color bar, this is the automatic one, you just define the object of the color, the object where you want to show the color bar from, and the axis, and that's it. But you can also do like scientific notation, and then you have to say here the format of the string that you want to plot, okay? And also you define the ticks. If you don't put the ticks, there might be like too many values shown, and that might be a little bit too messy. It might be like a lot of values, okay? Okay, or the other way is to call the matplotlib formatter, and then you just have to say that you want like the power of like 10 to the minus 4, and then you can put it for the color bar. Yeah. Okay. Then the next one is the contour Fs. Here again, it's the same function as before. You just have to change between P color mesh, contour F, contours, and so on. And here the labels, the levels. You define them as an array that goes from minus your lowest point to the highest. With some spacing, I chose 20. Okay. Yeah. Already? 3:50. Okay. So if you want to have a coffee break, now would be the time. We haven't gotten very far. How is everybody following? Could we speed up, or is like a good pace, or are you like, could you follow everything so far? Yeah, kind of. I am very fast. Yes. Okay. Okay, the rest you can just go through the notebooks. And if not, you can go to have some coffee and do a break. Yes, I will be here anyways. Okay. So I will continue explaining a little bit more. Hope everybody can follow. If you are not set with your content environment, just look at the screen for now and we come to you and settle everything, okay? Okay, so we have seen this plot here was just a funny function that Matplotlib also has, which is like with some hex pins, it's called. This is hexagons instead of squares. You would actually use it like a scatter plot, but because our hexagons is more filled, right? But it's just I never used it. Okay. Okay. And now the last part from Matplotlib is to give some texture to your figures, because of course you need some kind of plasticity to the figure, no? So it looks nicer. It's maybe, you don't always use it, but instead of having like blue, red, blue, maybe with some shading, some texture, it looks a little bit more like a rough sea. Okay, so what I'm doing here, you see the differences already, right, of the different plots. So this is the one we learned already how to do, like a color map data with contour fields. And now you can change a little bit the illumination or the intensity, so you start having some kind of roughness on the surface. Then you can put some, just massage your function a little bit, and then you get some, what you would say like a rendered figure. So it has some volume, at least to the eye, right? It seems like it's going up and down. So it's kind of the surface of the sea, okay? Depends on which blend mode you use, you will have it more or less. Like this one is overlay, then it's quite low, but this one is quite perturbed, right? Okay, so I can explain a little bit the function. So for this shading, we will use the light source, which will just put some light on the plot from one side. Now this is just the color map that we are defining is just blues. And then we do some, this is the value or the quantity that we are going to plot, which is like the speed of the flow. Again, we define the subplots. So it's 2 columns, 2 rows, so in total 4 plots. And here I'm using like a for loop just to define the axes as we did before. So I'm saying basically that for each axis that is inside the axis of the figure, we are putting no x ticks. Okay, so I'm eliminating the labels of x and y. And then I would put like a source, like a light source with, you define some azimuthal angle, or the other angle is just, you know, X and Y position basically from this light, how it's going to come on the plane of your plot. Okay, and then the different plots, right? So this is the upper left is with IMSHO instead of contour Fs, or P color mesh is another one, which you can just, IMSHO is fine. And as you see here, I only stating Z. So that's, I'm only saying what is the color map values that I'm gonna plot. I'm not saying anything about X and Y. So it's not gonna know, it's gonna work on the basis of the indices of this array, but not on the actual X and Y dimensions. If not, you can put X, comma, Y, comma, Z, right? Okay. And then you put the labels. So here I'm just saying this is the color map data. Now the second one is, well, with this function here, I'm just saying I want this shading to be shown, right? As I'm showing here. So I'm putting some light on the plot with some intensity, basically. This I have defined before, okay? And then the next one is the shade. The shade that I'm gonna put on the data that I want to plot in the rendered kind of plot. Okay, so this RGB is, you can think about it as a rendered image that you are gonna show with image show. And the rendered image, what it's saying is that it has some shading from a specific angle, which you are blending with some function, some mode. Hey, HSV is the one that I decide to use here, and with some intensity basically. And then it looks like this. So this would be, I don't know if you have used something like Unity, for example, then you have always to do like normal modes of normals basically of your the data that you're getting, and then the normals are saying how far, or this volume that you are perceiving from the image, how large it should be, and it's basically of the value of the pixel in the image. Okay. Yeah, and then the second one is basically the same. I'm just using another blend mode. Okay. Yeah, and it depends which one. The blend modes are better for specific things, others for others. Like this one might be, the left one would be very good for topography, for example. Then you want really to show, okay, here there is a mountain or whatever, and then the shading is better. It shows more kind of this volume of the object. Okay. Okay, and the last one is, this is the first 3D plot that I'm showing. So this is kind of cheating a little bit because it's not really a 3D plot. So I'm not showing X, Y, and Z for some vorticity values or speed values. I'm showing X against Y, and then the Z axis are the speed values. So you see here the labels of the Z axis is U square, V square, and then the square root. So the height of these kind of mountains that you see is actually the speed, right? Which is also color coded. Okay, so if this is done with the function which is called plot surface, and then you put X, Y, and Z being Z your speed values. And then you say that you want it to be at a specific, like the vertical, like yeah, this vertical isn't the same as the color map. And these are just some arguments that you put in, which are saying, well, this is like the rendered plot that I showed before that you are applying here as well. You're choosing anti-alias to be false. That would be depending on the resolution of your image compared to the resolution that your computer can have, and you have to play with it. And then I say I don't want shades because I'm already putting like a rendered image. Yeah, and then the rest things are just specifics to the plot. So it's just the X label, Y label, Z label. I'm putting the map of the colors as blues. And here I'm just saying where to put the color bar, the location, the size, and so on, and just plot it. Okay. I hope you followed. And you can try to play with it, maybe create a similar plot, but with another kind of, yeah. I mean, the NetCDF has U, V, W, it has buoyancy and pressure. So you can play with it and try to plot, I don't know, maybe the buoyancy of the field, and maybe you get an image like this. Okay, maybe play a little bit around. The next one will be already with X arrays. Hello, it's not changing. Okay. Yeah, if any questions, raise your hand.
Okay, it's time for the last part. Hope you're enjoying it so far. Now we reach into a different topic, and what we're now going to work on is unstructured data sets. And what you typically know from Earth system models, you know probably MIT GCM outputs, and then those ones you have on regular data, which is evenly spaced data depending on the on latitude and longitude. So you have 0.1 degree of, you have 1 degree, you have half a degree, quarter degree grids, and you can see those ones. You can also see immediately why it has problems, because we have a sphere and we cannot have a sphere projected onto, well, we can project a sphere onto a plane on a plate carrier, but we see that the lines deviate. So, and then we see singularities at the poles. So the poles are very poorly represented. There's other types of grids. For example, I think MIT GCM nowadays have 6 poles or 4 poles, so they define them differently. There's also some intelligent versions to work with regular grids, but some people say it makes more sense to switch to unstructured grids, and that's the strategy of Icon and FESM, like the big German Earth system models. And well, with unstructured grids come different problems. They have, for example, the unstructured grid we use is an sorry, it's a complicated word. It's a isohexaeder, I think is the right word. It's like so it looks like a diamond and has many more poles. And then the subgrid level, you have triangulars. So you have triangulars on the lower levels. And those are unstructured grids, and you can easily adapt those grids to do a grid refinement, to adapt the grid to coastal lines and coastal areas. So there's many advantages using an unstructured grid. But the disadvantage is that typical plot evaluations, what you could see now before, doesn't work so easily because they're not regular. So what you could see in the dataset Pablo gave you, if you open the X-array file, what you could see is that the dataset has 250 steps in X direction and 250 in Y direction. And those ones you can easily plot without big effort. So you can use X-array internal functions to just give a quick plot. When you have an unstructured array, you have different problems. And then now I want to show you a few ways to visualize these problems, these data sets. And on top of that, the data sets we are using, they're extremely large. So we have 70 million cells per layer. So you have 120 layers. You can already compute on your own how many cells you have them per layer. And then you have many variables. And then you have the ocean and the atmosphere. So these data sets get into terabytes and terabytes. And sometimes a single a single array, it's all saved as an array, can be too large for your memory, so you're not even able to load it into your memory. So you see why we need new strategies to overcome these difficulties, especially when we go towards more 1 kilometer resolution climate models. You already saw now X-array, and X-array is inherently using DASK. The idea of X-array is when you open a data set with X-array is that it's opening the data set in a kind of lazy way. So it opens the structure of the data set, but it doesn't necessarily load the data into the memory. So you have the shape of your structure, and then you can have 112 vertical layers. You have each grid cell has 70 million grid cells. Then you have 20 variables, and you have a time series of 5,000. This you could never use, but you can already see it. And normally, when you work with data, you see that it often boils down to something which you can visualize at the end. So you select an area, you select a time step, you select a variable, and until you're going down there, or you do computation on the way, until you're going down there, the data set becomes very small, especially when you only look into a region. So, but let's get into the notebooks. And I assume that most of you know scatter plots. Scatter plots, everyone uses scatter plots already, I assume. It's like, what do you need for scatter plot? It's basically your array, your string, and then connected to the string you have 2 more arrows giving you longitude and latitude. Here it's center longitude and center latitude. So what you can see here, what I opened here is the grid file, which I hope most of you were able to download. And when you look into the grid side, we have even the vertices, the center longitude. For now, we only use the center longitude. So you imagine a triangular, and in the center of triangular, that's your coordinate for each cell. So we have roughly 70 million grid cells. And for each cell in our array, because we have single arrays, for each cell we have our center longitude and center latitude. And when you have that information, you can already do a scatter plot. And if we now load the data set, this is just a snapshot, which you can see here. There's a couple of variables here. You can also, for sure, choose different ones. So if we now define our longitude array and our latitude array and our data array. So yeah, you select, it's basically, yeah, this is simply selecting. So now this is the temperature array of a single layer, horizontal layer, and we have all the information we need because we have the grid data. And then a scatter plot would be simply giving us the X and Y information and our data array. And what you can see here is a map. And what happened now is that in our scatter plot, all single cells, each single cell were plotted as a dot with the color of the value, here the temperature. And you can see this looks already kind of nice, but when you figure it out yourself, this will take roughly 5 to 6 minutes to compute all the dots. And that doesn't make so much sense. There's a simpler version to that. When you look here, you can select every X step. Here's every 14 steps, so I'm boiling it down. And the unstructured array, of course, has some structures inside. So it means you can subsample your data set, and then you basically still cover a large region. So it's kind of organized also. And this goes down then to 30 seconds. You can see that. But you can see already on the pole regions that the plot becomes less beautiful. And it's because, of course, we have less dots in those regions. So you can see already the first limitation of a scatter plot. Because when you in some region have lots of points and in some region you have less points, you end up with something which looks like this, like a carpet at the end. So yeah, that would be a scatter plot. That's not what we're going to do today, but this would be the easiest way for you to handle an unstructured array. It's like, so you have your grid information, you have your array, and you have a look how it looks like. So you get familiar with the data. what I wanted to show you now is, yeah, there's some interpolation here, so you can have a look there too. That's not so important for now, and there's also a way to show projections onto, for example, onto a sphere, what you can see here. But this we skip for now because we don't have so much time. So let's get more to the more interesting parts. There's another tool which is called Data Shader. And Data Shader, it's this module which you can see up here. I hope you can see it more or less. So yeah, that's the Data Shader. So you load the module, and what the Data Shader basically does, okay, you need to reformat your data a little bit to have it in the structure because it uses pandas as a structure. So you define in the pandas world environment the variable, the x value and the y value, which would be basically the same information you put into your scatter plot. So what you can see here is again your value. It could be here's the temperature again, temperature array, longitude array, latitude array. And then you can already define a region which you want to focus. Maybe that's not so important for now. If you don't, yeah, we want to look at the whole map, but later we will see also what happens when you look to a close-up. So yeah, then you basically can use a data shader. And what happens in the data shader function is basically it's working like a histogram function, which puts a bin on a regular kind of grid and searches on your array which array has a suitable value in that bin. So as soon as it finds something filling that bin, it stops searching there and goes to the next region. So it's quite efficient, and it does not need to find all the points. So when you have a region with lots of points on your in your unstructured grid, it would get some values, and that would be sufficient and would move on. So it doesn't need to load all the values. And so what you can see here is a plot with a data shader. And when you play it out on your own, you will see that this is already only a few seconds, and it already overcomes most of the limitations that we didn't need to sub-select data. And we also have a much more, even the poles are represented better, except from the very upmost part. That there you can still see that it's there. It's a bit problematic, but that's the poles itself. And yeah, so this would be an increasingly speed up. You can play around with this basic plot. There's also a way to go from the basic plot to do projections. So you use a data shader and projections with Car2Py. You can combine that. There's a nice function here below showing that. So this is a projection where you can see, yeah, where you can combine data shader with Car2Py, and now we have a closer selection. And what you can see, I do a different selection. And now if we would zoom in the first figure, which was showing the global map, you would see gaps in between when you zoom into this figure now. But it was showing only as many pixels as we needed to see for the whole map. Now we have a zoom, and now the bins are selected differently. So the thresholds are different ones. So now it finds for us the data from our unstructured array in a certain region which are relevant. So this is also quite quickly done and easily to see. Then we can say like, okay, let's go further. Okay, here's projections. Pablo, did you cover projections? No. No? Okay, then, well, I changed the function here, what you can see here. So you add projection to data shader, which is basically, yeah, using Car2Py projection and transformation, which you can see here. And this is what you plug into your, well, this is how you transform your data before. So you can use it this way. And you can use many types of projections. I just put this little example so you can do, here's the names of the projections. Small, wide, I have complicated names, by the way, but it's like, yeah, you can see projections of many types and you can use it in combination with the data shader. And, or the whole sphere, it's like, so you have this type of projections, you can play around with that if you like. But then when we say like, okay, let's go to even closer to the data set, and then you will appear at a certain point, you will arrive at something like this. So what you see now is that the bin size doesn't suit anymore. And this means we are arriving at grid size, and at grid size, the visualization with data shader is, as you can see, not the first choice, because we can see that it fills in some points here, but they're way too less, and so we have gaps, and we see that close to grid size it's complicated. You can stretch that a little bit by doing some interpolation schemes on the grid size data. You can see that here it gets a little bit better, but yeah, that's not the most optimal way. There's some parameters you can play around with to change that, and that's in the data shader. Is this kind of lambda function which kind of spreads the pixels around the selected pixel in the bin. So it's there would be a way to kit that. I don't recommend that because I think that's going more and more far away from an interpolation you want to use. But this is mainly also only to show you the limitation of the data shader in this size. Which then brings us to our third version of visualizing the data, and that would be plotting immediately on the triangulars. So what you can see here, where do we start? Is, so yeah, you can, if you go back to your unstructured grids, you can see that you have triangulars and you have information for the triangulars. So you have your vertices and you have your edges and your cell centers. So you have information about the irregular grid you normally use. And you also have information about the vicinity. So this is called vertex of cell. So what you can do is basically using a matplotlib function for triangular meshes. And when you feed this function, this object function, it gives you a triangulation object. And you can feed that with the information you need. So your center longitude, your vertices, and your vicinities of the data. This is what you would need from your grid. So this is what what would be required to do this thing. But when you have unstructured data sets, you will have always a grid file where these variables are supported. So if you use other unstructured grid models, they will provide you with this information. So that would be accessible too. And yeah, and this function, this basically gives you your triangulation object. And what you can then do is use the triangulation object to plot every triangular in your domain. So what you can see, where do we have it? Yeah, here would be an example. So you have a simple matplotlib figure. You have then a new command, which is not shade, which is not p-color mesh. It's also from matplotlib. It's called tripcolor. And there you plug in your triangulation object and your selected data set, which is the result from the function you could see before. And this enables you to, well, this is just configuration for the plot. I think that's kind of trivial. But yeah, what you could then do is plot on the triangles. When you have a larger view, you don't see so much different compared to the data shader. Although I think even on this one you can see, if you look closely, you have more structure in the details. It really depends on the how do you call that? It really depends on which region you want to look at. Is it a close-up or not a close-up? What do you want to focus on? But normally you have an overview figure and you have a close-up figure, especially if you want to look at specific physical processes or you want to visualize something like a filament, a frontal filament or something like that. If we now go closer, you can see this is the same region. Wait, I have a better one, sorry. Yeah, this is the same region as before, where the data shader seemed to fail on the lowest level. So you can visualize the triangulars, and when you look closely, you can already see triangular structures in the data. If you go to even closer data set, oh, I don't have, well, you can see here on gradients, you can see that maybe even faster. You can see that it's going to triangulars. You can try yourself to even make to even go closer, change the longitude and latitude range, and then you can see that you really see single triangulars of your original mesh. So the advantage or the beauty of this is that you really plot on the native grid your original data. So this is really what in your computation is done, and there's no interpolation or anything like that done in between. So this would be very beautiful. But of course, you could also maybe notice already that I don't show the whole world here anymore, because when you plot each triangular, you have the same problem like scatter plot. You don't want to plot all the triangulars if you want to show the whole world, because then you end up with 70 million grid cells, and your computer, in best case, maybe shows 10 million pixels. It's like, so you would end up with an overload, and it would take too much computation. So plotting on triangulars of this type of mesh makes sense for close-ups and features, and to really see the values on the grid. So this would be the third way to visualize unstructured data. Another way would be more bridging towards what we had before. There would be interpolation schemes. And what you can see here is basically a way to go from your grid data, from your longitude and latitude array, from your unstructured grid to a regular grid. And the basic idea is that you define a new regular grid, for example, a quarter-degree grid. You define it yourself, or you say you want to compare to a climatology from Argo, and then climatology from Argo has also a grid. You can use the regular grid from this climatology, for example, and you can say, I want to do some evaluation, I want to do some bias maps or whatever. So you could compare it, and then you say like, okay, how do I get from my unstructured grid to a regular grid? And in this script, you can see how this works. And well, yeah, it's kind of very simple in the way of, you probably know mesh grids. You just create an array depending on your resolution, which creates a regular mesh. Here it's, in this example, it's a quarter-degree. You create your mesh. You change your 2D data to 1D arrays by flattening them. And yeah, there's some changes from radian to degrees. That's not so important. There's also a transformation from spherical to Cartesian data, which is a minor step. It does not always depend, but in some cases it depends. You don't need to worry so much about that step. And then this is what is happening here is basically the query. So it's the idea of this interpolation scheme is like different ones you do a kind of nearest neighbor approach. So that's what's basically happening in the lowest level. So you have your unstructured grid, and then you have your regular grid, which you defined before. And now you want to find to each regular grid point, you want to find your nearest neighbor from the unstructured grid. And this is basically, that's a SciPy function. And yeah, it's like, I cannot tell you so much about the function because I didn't build it myself. It's a SciPy interpolation function, but what you plug in is your regular grid as an input, and you run it over your native grid, and then you find your closest grid neighbors. And so this returns you your data set interpolated to, this returns you the indices which you need to select from your unstructured grid. So yeah, so that would give you a run, would give you the names. Like imagine you have an unstructured grid, and then you have regular grid files in between, and this would give you the indices correlating with the regular grid file. And what is called then here interpolation is simply applying those indices, which you can see up here probably. Where is it? Interpolation, apply grid. Oh no, sorry, it's the apply grid. Yeah. So here would be then an example. You could see you load your grid file, you load your data. Here I used the horizontal kinetic energy from on your native grid. And then because you already calculated the indices on your to connect from your irregular to your regular grid, you can use that. You don't need to do that every step. That's also an advantage. So because your grid, your unstructured grid doesn't change. So you can use, once you have done the computation, you can at the end only select the indices from your unstructured grid arrays. So you load your data set. Here I have an example, and then you apply your grid. And what you put in is the new indices from your grid and your data set. And what it returns is basically the selected, here in this case, the horizontal kinetic energy, and it selected the points already on your regular grid, and it returns this in a 2D format. And the beauty of this is that if you go over time series, you don't need to do interpolation all the time. You just select the data, and that's why it's quite efficient and fast. And also the query itself is quite fast. The SciPy function is quite powerful. And yeah, what you can see here then is that you can use the before mentioned visualization types like p-color mesh. So you have your data set on a regular grid file now, and then you can see how you visualize it that way. So you can use the strategies you already know. So you have your unstructured grid, you interpolate it to a regular grid, and then you can apply what you already know. So you would not be completely lost with that type of data set. And the nice thing is that it does not need to be an icon grid, because here's the example, an icon grid, but the way the code is written here, it doesn't matter. You can also apply the same technique to Argo dataset. It's like you can have any other unstructured grid, this query, and here's neighbor interpolation works always the same. It's not stick to this data set. So I'm using icon data here, but it's independent from icon data, the techniques you can see here. So this brings me already to the end. I also prepared a cloud data set. I fear that the internet connection is too slow here. I don't know why exactly, but you should definitely have a look on this function. What we use also in the icon world would be a lot of cloud computing. So these huge data sets, which is hundreds of terabytes, which we don't store on a personal computer, it's impossible, but which we store and share because we have collaborative projects. Those data sets you would the new strategy to share that is an intake catalog. I don't want to go too much in detail here, but it's basically a JSON file which has a library hosted on a server, which you can then stream, and this in combination with Xarray and Dask. So you can access the dataset without loading the dataset, and then look around how the dataset looks like, and then you can download or stream the dataset you at the end want to look at. And I prepared the dataset. My big hope was that we could use this in this workshop, because this dataset is having lots of variables. It's a coupled simulation one. I think it's 5 kilometer simulation one from the ERI project. I can also supply you later with more information, but you have atmospheric data, you have ocean data. It's really a large data set. Maybe you can try to use this intake catalog, select your own variable, and one task would be, or what I would suggest to do now would use one of the techniques. You could see data shader, interpolation, or on plotting on triangular grids, and do a short animation. Pablo showed you how to do animations, and now the challenge would be do an animation on a triangular grid for a short time series, something like that. And you can use the intake catalog. If the intake catalog is too slow, the data set you downloaded before, there's one called, I think, SST time series, another, I think, is even larger, has more data. There's few time steps you could apply the same things. This is just a backup if the intake catalog doesn't work. But yeah, give intake catalog a try, make a visualization, maybe on a projection, on a sphere, or maybe on a close-up with triangular mesh, or just try out the way of visualization you want to do. And maybe we still have time at the end to show that. I see the time is short, but maybe one or the other manages to do that in time. I'm speaking too much. I'm very sorry. Okay, please go ahead. One more remark. When you start, when you look into the notebooks, you see the modules. Those ones you can load. What you then have, the load part with intake, you skip that part. Because open from download, that's what we do for now. It's like, so you start from here, because this one will cause some problems now for you. So, but that's why we have the alternative option, open from download. Just skip over the first part and it will work. And if you want to do the animation, there's a 2 GB dataset, which is a time series of the SST. That's maybe the simplest way to do something. If you have downloaded that already, you can decide about which method you want to use and which region you want to visualize and what kind of projection, and then just make a little animation, and maybe later we can share on Zoom here. Okay.